In this video, we'll be solving systems of equations that end up having an infinite number of solutions. So let's solve by using either Gaussian elimination or Gauss-Jordan elimination. Personally, I prefer Gaussian elimination. I'd rather do the less row operations and then the more work at the end to back substitute. I think the back substitution is less work than getting it into reduced row echelon form. Okay, so if I'm shooting for row echelon form, my first column looks good. Leading one first row, first column, zeros below. The next thing I need is a leading one second row, second column. So we're going to turn that 2 into a 1. The row operation we're going to use for that, we're going to multiply through by a half. 1/2 times row 2 for a new row 2. I'll write my first and third equation down since it's not changing. And now let's multiply row 2 by a half. 0 times a half, 0. 2 times a half, 1. 4 times a half, 2. And 20 times 1/2, 10. Now my second column looks good already. I have a leading one second row, second column, and a 0 below that. The next step in our Gaussian elimination says leading one third row, third column, but notice that we have a 0 there. So this might already be in row echelon form. Let's go through our characteristics. If there's a 0 row, it's at the bottom. Well, we do have a 0 row, and it is at the bottom. Characteristic 2 says the first non-zero entry coming in from the left is a positive 1. That's also true. Third, leading one in the row above needs to be farther to the left. We have that as well. And lastly, below all leading ones must be all zeros. We have that as well. Our matrix is indeed in row echelon form. That means that we're ready to write our equations and then back substitute. We get the equations x minus 6y plus 9z equals -8. Y plus 2z equals 10. And our final equation is 0 equals 0. Now we've seen some before that gave a false statement, 0 equals 4. But this one here gives a true statement. 0 does equal 0. Anytime we're solving any kind of equation and we end up with a true statement, that means that there is an infinite number of solutions. So it is true that there is an infinite number of solutions, but we can be more specific about that infinite number of solutions. Just so that we can draw a picture and have a better understanding about what we're going to do next, I'm going to switch my thought process to a system of equation involving just 2 equations and 2 variables. Let's think about what the graphical interpretation of infinite number of solutions is in 2 dimensions. When you have an infinite number of solutions, and we think about that graphically, that means that we have the same line twice. That's why there's an infinite number of solutions, because there's an infinite number of intersection points on that line, because there's an infinite number of points on the line. So there is indeed an infinite number of solutions. However, that does not mean that every point on the Cartesian plane is a solution to this system. We have all kinds of points all over the Cartesian plane that do not fall on those lines. So what we want to do is narrow down the infinity. There are different sizes of infinity. There's an infinite number of points on the plane, and there's also an infinite number of points on that line. However, the number of points on the plane far exceeds the number of points on the line. So what we want to do now is narrow down the infinity so that we're only talking about the infinite number of points on that line. The way that we're going to do that is by writing what's called a parametric equation. You'll deal with parametric equations when you get into a physics class. So these are our steps for writing the parametric equation. First, you want to let z be equal to t. Then we're going to substitute t into the equation containing y and z for z and solve for y. It's really the same thing that we did when we got a number as a solution for z. We would take that number and plug it into the other equation and solve for y. Well, we're going to do that exact same thing, except we're going to be plugging t into the other equation for z and solving for y. All right, I'm going to rewrite my equations that we have. X minus 6y plus 9z equals negative 8. Y plus 2z equals 10, and our 0 equals 0. All right. So the first thing I'm going to do is state that I'm letting z be equal to t. There's our first solution. And now, just like before, I'm just going to take what z is equal to and plug it into my other equation and solve for y. So we are still back substituting. This is going to give us y plus 2t equals 10. And then solving for y, we get y to be equal to negative 2t plus 10. There's our second solution. The last variable we need to solve for is x. We are going to plug the t into the equation containing x for z, and then we're going to plug this whole thing, negative 2t plus 10, into that other equation for y. Now, since y is equal to a binomial, be sure to put that in parentheses when you substitute it in. We're going to have x minus 6 times this whole thing, negative 2t plus 10, plus 9 times t equals negative 8, and we'll solve for x. I'm going to start by distributing. I have some like terms that I can combine. And then I'll move that 21t and the negative 60 over to solve for x. We get x to be negative 21t plus 52. There's our third solution. And like any answer to a system of equations, we want to rewrite this as an ordered triple. I know it looks weird, but be comfortable with it. It's okay to have algebraic expressions for our variables. We end up with the ordered triple negative 21t plus 52, negative 2t plus 10, and t. Let's try another one. All right, we have another augmented matrix. Take a look at this. It is already in row echelon form. I really just want us to practice writing the parametric equations. So we are in row echelon form. I'm going to start by writing my equations out. Y plus 12y minus z equals 0. Y minus 5z equals 9. And lastly, 0 equals 0. There we have a true statement that tells us that we're going to have an infinite number of solutions, but we want to narrow down that infinity. The first thing we do is let our variable z be equal to t. And you may wonder why we're using the variable t there. In physics, when you're going to see parametric equations a lot, the parametric equations are always based off of time, hence the variable t. In some math books, you'll see them use other variables other than t, but since this is what you're going to see in the future, I like to just show you that from the beginning. All right, so z is equal to t. There's our first solution. And now we're ready to plug that t in for z into the equation above. We'll have y minus 5t equals 9, making y equal 5t plus 9. There's our second solution. Lastly, we need to solve for x. So I'm plugging t in for z, and then that whole expression, 5t plus 9, in for y. So we get x plus 12 times this whole thing. I'm going to put it in parentheses. Minus t equals 0. We'll distribute the 12. That's 60t plus 108 minus t equals 0. There's some t's that we can combine. So x plus 59t plus 108 equals 0. And then we'll solve for x. X equals negative 59t minus 108. There's our third solution. And the last thing we need to do is write that solution as an ordered triple. We get the answer, negative 59t minus 108, comma 5t plus 9, comma t.